All right, let's take a look at paper number 1, problem number 12. It deals with some sequences. A and the common differences. The first term would be plus D, plus 2D, etc. So before I've even gotten to the problem, it's a good idea, any sequence problem, just start writing out the terms so you can take a look. We have another sequence, V sub n, which is defined as 2 to the U sub n power. So in other words, each term is going to have a 2, and the power is sequences terms. So we have 2 to the A, and then plus B, etc. A plus 2D, and so on. All right, now let's jump to the question. Part A, number 1, show that V of n plus 1 over V sub n constant. Well, let's looking at V sub n, if we put that over 2 to the A, exponents, and you get 2. Let's take the third term, which is 2 to the A plus 2D, over the previous term, 2 to the A plus D. Again, if you subtract the powers, you're going to get 2 to the D. 2 to the D. All right, so this is part A, number 1. So we show that it's constant because that ratio is always 2 to the D power. Part 2, write down the first term in the sequence V sub n. I think we've already done that. So it's up here, and we don't have to do it again. We'll just write down that answer, 2 to the A. Part 3, write down the formula for V sub n in terms of A, D, and N. Well, looking at V sub n up here, it is. It looks like the formula every term of the sequence. So let's write 2. Every term of the sequence has an A in it, and then plus some multiple of D. Well, the D depends upon the term number. For example, the first term, there is no D. The second term, there's 1 D. So first term, write a little table up here. The first term, D is 0. The second term, 1D. The third term, we have 2D. So you can see that the D is always 1 less than the term number. So to write that, we'll just go M minus 1 times D. So here's your expression for formula for V sub n in terms of A, D, and N. So V sub n equals 2 to that power. Okay, part A is done. For section B, they're saying let capital S of the first n terms of the sequence written down there. And if you observe V sub n, you can tell that it's geometric. Multiplying each successive term by so this geometric, you can go to your first term, rate to the power minus 1 over the rate, or the common ratio, minus 1. So you just all you have to do. For the first term, we already know. The rate, as I just said a couple minutes ago, is 2 to the D. That's the common ratio as you move to the right in that geometric sequence. But we have to take that to the nth power, so it's 2 to the D, n, minus 1, all over the rate, 2 to the D, minus 1. And that completes part 1 of section B. Part 2, find the values of D for which sum, or the series, exists. Well, since we know it's geometric, the geometric infinite series, when R, when the common ratio, the absolute value is less than 1. So if the common ratio is less than 1, then that sequence converges. So we got to figure out what the value of D is that will happen. Well, we know it at R is 2 to the D. So the absolute value of 2 to the D is going to have to be less than 1, which means we 2 to the d has to be greater than -1 and less than 1. Well, if you think about this, 2 to the d is always positive, so we don't really have to worry about the negative part of this. Just to know that 2 to the d is going to have to be less than 1, and we want to solve this for d. We want to find the values of d that make that true. So to solve this for d, let's take the log of both sides, so we get d log 2 is less than log 1. D log 2, and the log of 1, of course, is 0. And then divide both sides by log 2, so d has to be less than 0. So those are the values of d that'll make that converge so that the series exists. All right, let me clear a little room here and do part 3. All right, part B, number 3, write down the sum of the infinite series in terms of a and d. Well, the sum of an infinite geometric series is the first term over 1 minus the r. Well, we have all that information. So the first term is k. Common ratio is 2 to the d, so it's 1 minus 2 to the d. And that's it. It's pretty easy. And then finally, part 4, given that infinite sum, given that the sum of the infinite series is equal to 2 plus 1, find the value of d. Well, this is the formula for the infinite sum. So we set 2 sum. They're saying it equals a plus 1. And all we have to do is take that little equation and solve for d. Well, let's see. How about the first thing? Let's write this a little bit better. 1 minus 2 to the d. And the right-hand side, 2 to the a plus 1 is the same as 2 to the a times 2. Looking at this, you can divide both sides of that equation by 2 to the a, so we get 1 over 1 minus 2 to the d equals 2. Trying to solve for d, so I'm going to reciprocate both sides. 1 minus 2 to the d equals 1 half. Subtract 1 from both sides, negative 2 to the d equals negative 1 half. Make both sides positive, 2 to the d equals 1 half. 2 to what power equals 1 over 2? Well, that would be d equals negative 1, because the negative 1 power flips it over, so the value is negative 1. All right, the last part of problem 12, we're given, they define them. We have geometric in the first question. Common ratio is q, so we multiply by q, multiply by q again, and so on. And the other sequence is called natural log of the previous sequence. So it's going to be the natural log of p, comma, the natural log of pq, the natural log of pq squared, and so on. Now let's look at the question. Find the sum of. All right, so we know that the second one, just looking at it, we just want to observe the fact. Well, let's write this out. If we're trying to, that would be ln plus ln pq plus ln pq squared plus, and let's take a look at this and see what, if we can see what the pattern is, like we did previously. Well, every term is an ln p and q to some power. Now, what's the power on the q? Well, like those previous sequences, the q is 0 power on the first term, first power on the second term, second power, so the power is less than the term number. So if we write out that last term in this form, then we know that the sum of the sequence is going to equal the natural log of p to the n q to the n minus 1, where n, got to change my variables. So find the summation.